Thank you for the opportunity to present to you about horizontal line drive selective solution mining. My name is Quentin Hardage, and I am one of the inventors of HLD technology, a technology we believe will revolutionize the solution mining of potash in Saskatchewan. Before we get started, just a little disclosure. This disclosure highlights that this presentation as presented contains forward-looking statements that may not come to fruition. It also includes future-oriented financial information that may not be met. Any potential investor should complete detailed due diligence and form their own opinion before proceeding with any investment. So a little history. My co-inventor Steve Halliburton and myself have been discussing mining potash more like an oil and gas development for some time. We have significant experience in solution mining and oil and gas, including with Invictus Minerals, North Rim, Potash One, K+S, Rallymont, Prairie Hunter, and Admiralty Oils. We have a strong desire to produce potash more like an oil and gas project, like SAGD or waterflood projects that we've worked on throughout our careers. We also really realized that due to the limit of available fresh water in Saskatchewan, potash mining, solution mining had to change. We've completed extensive research on several solution mining pilots within Saskatchewan, mainly the Lumsden pilot, the Lynbar pilot, and the Patience Lake conversion to a selective solution mine. We've also completed an enhanced oil recovery research project for the U of S that focused on SAGD and water flooding. What HLD technology is bringing all of this experience together and creating a mining plane solution mining, which is different than what is done in the industry today. Today, all solution mining is done with caverns formed using fresh water. So let's go through some of the pilots. The Lumsden pilot was the first pilot that we researched. The vertical injection well was drilled in December 1966, and the vertical production well was drilled in April 1967. And that well was approximately 100 meters northwest of the vertical injection well. By pumping at high rates of pressure, they were able to create an elliptical mining surface between wells, and they were able to successfully communicate these vertical wells. And what that means is they were able to pump brine down the injector and recover that same brine at the producer. They also used a tracer so that they could showcase that this was in fact the same brine that they were injecting that they were recovering. They completed several important solution mining tests, and that included solution mining with saturated brine, which was very unique because when you mine with saturated brine, it only wants to seek out KCl because it is fully saturated with NaCl. Therefore, it stays within the high-grade KCl deposit. This pilot produced over 20 tons of potash and was deemed as successful. However, Lumsden Potash was owned by a U.S. oil company, and when the prices of oil skyrocketed in the late 60s, early 70s, the pilot was abandoned. The Lynbar pilot. The vertical well was drilled in January 1967, and the vertical production well was drilled in November 1967, approximately 125 meters north of the vertical injection well. These wells were connected by pumping at high pressure, over 34 MPa, to create an elliptical mining surface between those wells. There was a very detailed account of the work that was done on this pilot, and we were able to find out that the working injection pressure of about 15 MPa was used to inject brine in one well and recover it out the other well. So this was a closed loop, high pressure system using man-fill brine. They tested various temperatures and were able to record several concentrations of KCl throughout the pilot's life. The Lynbar pilot was recorded as a success after a 6-month test. And we interviewed several witnesses that highlight the success of the system. They even mentioned to us that there was a product storage barn on site that contained bags of potash at the end of the 6-month test. However, due to insider trading charges and foreign interest from Poland, a mine was never built. So what I'd like to show you is basically what these two companies were able to do. They injected brine down the center injector at high pressure and recovered that same brine at pressure out of the producing well. They created this elliptical mining plane through high pressure injection. No caverns were used during the creation of these mines because they use these elliptical mining surfaces. We also studied the Patience Lake pilot, and this study highlighted the importance of surface area. This was highlighted by Doug Roos, a very well-known solution mining expert in Saskatchewan. And that report said that the Patience Lake conversion would be successful because of the amount of surface area that was in the tunnels underground. We then realized that getting a lot of surface area underground was very important for the success of HLD technology. So we took the concepts from the Saskatchewan pilots, the Patience Lake pilot, and combined it with the latest oil and gas technology for water flooding and SAGD to create HLD selective solution mining. So as you can see, if you look at the left-hand side or the bottom portion of this drawing, you can see the injection well in the center and the producing well on the outside. Each one of these ellipses represents two vertical well pairs. We then added the third vertical well pair on the outside to create all of that. But what we realized was that by using horizontal wells and multi-stage injection packers, we could replace all of those vertical wells with 3 horizontal wells. Now, the one thing that should be noted about this drawing is that these horizontal legs are only about 200 meters long. When we test this in the field, we will use 800-meter long horizontal wells with packers spaced about 25 meters apart, meaning that we will create 50 times the amount of surface area underground as the Saskatchewan pilots that we researched. So as you can see in blue, we have the horizontal injection well, and on the outside of the horizontal injection well on either side, we have the horizontal producing wells. The multi-stage packers is what allows us to have these multiple ellipses of surface area connecting all of these wells. And how I knew we really had something special was when a gentleman by the name of Jared Galanzowski contacted us to join the HLD mining team. Jared has a vast amount of experience with cavern solution mining, both vertical and the first application or attempt of horizontal cavern mining in Saskatchewan. He saw our patent and decided that he wanted to join the HLD team. And that was when we knew we had something really special. So what is HLD mining? Well, it's a patented technology in Canada and the US. It stands for horizontal line drive selective solution mining, as per the picture I just showed you. What's unique about this is the creation of the mining plane through the use of multi-point injection. This allows us to create a significant amount of surface area, and it allows us to also lower our injection brine temperature. And we'll get into that further on in this presentation. It's a completely pressurized system. So we require pressure to create the mining plane, and we require pressure to maintain the mining plane. And this ensures that we have turbulent flow within the reservoir. This helps to maximize the dissolution process. The multi-stage packers give us even fluid distribution throughout the mining plane, and this limits or eliminates short-circuiting within the reservoir. And short-circuiting is one of the major downfalls of other horizontal solution mining technology. We are able to initiate mining with NaCl-rich saturated brine, so we do not need to use fresh or brackish water to create caverns underground. We can start right with NaCl and ensure that that NaCl-rich brine stays within rich KCl, because like I explained before, NaCl saturated brine does not want to seek out additional NaCl. It wants to seek out KCl so that the Na can drop out and be replaced by K+. Now this next part is really significant for our technology. We're planning on having an injection rate of about 100 meters cubed per hour per injection well. And if you were to put down 100 meters cubed per hour into one well and just inject it in one point, like the other horizontal solution mining technologies do, you would have a real hard time controlling where that brine goes, and that's why you get short circuiting. But because we use multi-stage injection packers throughout the whole length of the horizontal well, we're able to spread that 100 meters cubed per hour out to about 3 meters cubed per hour per injection point. And because we're able to do that, we're able to evenly distribute the fluid through the reservoir and not push on it so hard that we lose it to areas that we don't want to. So it's a very controlled way to move brine efficiently in and out of the reservoir. The other thing to highlight is that all of the injection wells and production wells are the exact same. So we can change any of the injection and production wells or vice versa at any time during the life of the mine. So let me give you a little bit of background on the patent process. It is a complicated process, and for good reason. You have to prove that the invention is unique, and it involves several rounds of scrutiny from the United States Patent Office experts. You have to justify uniqueness, and that is something that we were able to successfully do. So the horizontal line drive selective solution mining method was invented by Steve Halibura and myself in 2018. We filed a U.S. provisional patent application May 29, 2018, and we also submitted the full-blown U.S. patent application March 29, 2019. We submitted the Canadian patent application on that same day. The U.S. patent application then went public December 5th, 2019. And after several back and forth and interviews with the U.S. Patent Office experts, we were granted our U.S. patent on July 27, 2021. Our Canadian patent was then granted on June 14, 2022. So let's talk about the HLD completion, because this is a very significant part of the success of HLD mining. So as mentioned before, our horizontal legs will be approximately 800 meters long. They'll be open hole horizontal wells with about a 222 millimeter hole. The wells will be spaced approximately 100 meters between each of the legs, and for all, they will be parallel. The injection and the production wells will be identical and therefore will be interchangeable. We specifically designed a special multi-stage injection and production packer for HLD mining. These packer systems will have 25-meter port spacing, so approximately 32 isolated injection points along the horizontal well. They will have triple packer seal between each port, and each packer seal has 2 seal points. So there's 6 seal points between each injection area. These packers can also be inflated multiple times over the life of the well. The horizontal injection packers will also be equipped with multiple stainless steel sliding sleeves for isolation. So they will allow us to open certain ports and close certain ports. This will be very important for the creation of the mining plane. Once we created the HLD technology. We wanted to make sure that we had some real experts do some due diligence and a simulation model on the technology. So we hired Rembe Consulting out of Germany, and this was Michael Rembe and Norbert Gruschow, two highly respected consultants in solution mine modeling and dissolution chemistry. In fact, Norbert Gruschow has a significant amount of experience in dissolution chemistry for solution mines and has been involved in a number of successful solution mines. They modeled the brine flow between injection and production wells combined with selective salt dissolution, mass, and heat transfer. They determined that each well pair would have access to 900,000 meters cubed of potash ore, or 520,000 tons of KCl at a 29% average KCl ore grade. And we're expecting to target KCl ore grade significantly higher than 29%. They recommended the injection temperature be approximately 70 degrees Celsius for the most economical mining. And that's 20 to 30 degrees less than our other competition. And it allows us to use the geothermal heat gradient to heat up our mining brine. And we'll talk more about that later. And basically what it highlighted was that the KCl saturation from many different techniques. So for vertical cavern or dual well cavern, they can expect a 95% KCl saturation, but that is not continuous, and it involves locking NaCl saturated brine into a cavern for 4, 6, 8, 12 months to reach that saturation. Horizontal caverns, Norbert predicted, would be able to have a max of 75% KCl saturation through continuous injection and production. And the reason for that is just due to short circuiting. And then the HLD mining had the chance of reaching up to 100% KCl saturation with continuous injection because of the amount of surface area that we contact and the retention time and elimination or significant reduction of short circuiting in the reservoir. And that could provide a KCl concentration of up to 200 grams per liter. So in order to showcase our technology, we need to do a pilot, which we're calling the HLD Showcase. And basically it's so that we can showcase the strong brine that this technology will be able to produce. And we're going to do it very similar to an oil and gas type play. The pilot is going to run for at least 120 days, and it'll showcase the strong KCl brine, optimal injection brine temperatures, the operability of the HLD system. We'll also be able to highlight our Vortex Crystallizer and do some economic calculations on that, and it'll highlight the optimal pressure and rate. This will allow us to fully customize a full-scale development once we get there. We hired a third-party cost estimator, DMC Estimating, to provide us with a cost estimate of what the HLD showcase will cost. And for a 120-day showcase, a Class 4 cost estimate is approximately $23 million. You can see that the HLD showcase will involve the 3 horizontal wells, and then it will involve a crystallizer, a receiving tank, and numerous surface tanks for crystallizing out the KCl. This just goes into a little bit more detail of the cost estimate. Again, this cost estimate was completed by DMC Estimating following AACEI Class 4 cost estimating principles. DMC Estimating has significant experience working with other mining companies doing AACEI cost estimates for their projects. This is a plus or minus 30% cost estimate. This is the Vortex Crystallizer. The Vortex Crystallizer was invented by the same group as the HLD Technology Buffalo Potash. It's based on certain aspects of a spray evaporator, crystallizer, and direct contact crystallizer units. Basically, we realized that one of the limitations of other crystallizers is that they cannot adapt to the changing atmospheric temperature that we see in Saskatchewan. You know, some days it's plus 25, some days it's minus 25. And so we wanted something that was customizable to the ambient temperature. And so by using air compression and vortex tubes, we're able to customize the amount of cool air that is injected into the crystallizer and maintain kind of the similar ambient temperature within the crystallizer. This is a combination of evaporation and heat transfer to cooled air, and it results in cooled brine and precipitation of potash crystals. The circulation of the mother liquor is similar to conventional crystallizers, and we can add dissolution water as required. Slurry gets held up at the bottom, and that allows us to control the crystal size that is produced out of the crystallizer. And this is a patent pending design. And that patent pending was filed in 2022. The HLD Showcase Mass Balance showcases that every month we'll really produce potash or crystallized potash in the surface tanks besides July and August because it's too hot. The optimal window for operating would be November to April. And you can see that through the life of a 120-day test, we'll produce approximately 15 to 20,000 tons of product. We will also produce a KCl-rich brine that can be sold to the oil and gas industry for drilling activity. This just shows a simple closed circuit design for the showcase. So brine will come out of the production well. It will flow, production wells, it will flow to the receiving tank, and then it can either go into the crystallizer to be crystallized, or it can go into the surface tanks to be crystallized. The brine that is separated will go into an agitator where NaCl can be mixed in to ensure that fully NaCl saturated brine at 250 grams per liter is then injected back into the well at high pressure. As mentioned before, because we can, our mining fluid needs to be about 70 degrees Celsius, that gives us the option of using a closed loop geothermal heat exchanger to heat up our mining brine. This will lower the greenhouse gas footprint and really minimize our natural gas requirements. This is also our plan for net carbon zero for this project. So the HLD Mine Economics. Again, we hired a third-party cost estimator to help us put together these CapEx costs, and that was DMC Estimating. The CapEx estimated for 250,000 tons per year of MOP is $275 million. And then an additional $175 million to add 250,000 more tons per year by adding in an extra compaction circuit. Therefore, a total CapEx of $450 million for 500,000 tons per year of MOP. That's a CapEx per ton capacity of $900 per ton. We're expecting operating costs of about $70 a ton and sustaining costs of about $19.75 per ton. That gives us a 30-year 8% NPV of $560 million and a 30-year IRR of 30%. And we are very confident in our economic model. Our economic model was created by Randall Green, Buffalo Potash's CFO. Randall Green has a significant amount of experience creating economic models for both producing and proposed solution mines. And so he has been involved in a fair chunk of these economic models. And so he knows when the costs, what costs are accurate. And so we have a high degree of certainty with our economic model. What does HLD development look like? Well, it's going to be very similar to the evolutionary path as the Bakken development in Viewfield, Saskatchewan, and other tight oil water floods. You're going to start with smaller spacing and shorter wells. So the wells will be spaced about 100 meters apart with 800-meter legs. And as we advance in developing HLD technology, the spacing will increase from 100 meters to 150 meters to 200 meter spacing between horizontal wells. The horizontal wells will go from 800 meter horizontal legs up to 1600 meter horizontal legs, and will also alter our packer spacing. The whole goal is to increase the efficiency and reduce the amount of CapEx to produce the same amount or more potash. And we've seen that same type of development in the oil and gas industry. When they first started developing the Bakken, the well spacing was very tight, and now the wells are quite a bit further apart. Also, wells started short, and now wells of 1,600 meters to 3,200 meters can be seen in the Viewfield Bakken. And we feel that the HLD development will be very similar. So throughout this presentation, you've heard me speak of how HLD technology produces potash differently. Now, the MOP product that's produced will be the exact same final product, but what will be different is how it will be produced. HLD GreenPotash, which is a name that we trademarked because our product is produced differently, is a product that will be produced with no fresh water to create caverns and a negligible amount of fresh water to produce MOP. We'll use a closed loop geothermal heat exchanger to minimize our greenhouse gas intensity. All tailings will be left underground, and we will have a very small surface footprint. And for all of these reasons, we feel that we have a real strong ESG advantage, and therefore we trademarked HLD GreenPotash. There's several products that we plan to produce. HLD GreenPotash Fluid, HLD GreenPotash MOP Fine and Granular, and finally, we hope to get into HLD GreenPotash SOP, which is a real strong demand product, especially in drought conditions. I'd like to thank you for taking the time to listen to my presentation on HLD technology. Please feel free to reach out to me anytime if you have any questions about HLD technology and our plans moving forward. Thank you very much and have a good day.